resolvent algebra is some kind of replacement of the Weil algebra in quantum mechanics, which might be very well known to you. And this goes back to Hermann Weil, of course, almost 100 years ago. And the resolvent algebra is a bit more recent and was involved by physicists, actually. And the reason for that is that it has some properties which they like. And also, if you're a mathematician, then you may find it also interesting from a mathematical point of view. So I want to recall these two constructions and somehow compare these models. And then, and then I go to a concrete representation, which we all know very well, and look at the Fock Bargmann space and representation of the resolvent and also the Weil algebra. There's a result by Lou Coburn involved, where he looked at the Weil algebra some years ago. And I want to do somehow the similar thing for the resolvent algebra. And the resolvent algebra is an example of a shift invariant closed algebra. And there is this quantum harmonic analysis, which I guess by now you also saw several times, which is very well designed to understand such shift invariant algebras. And in particular, resolvent algebra is a good example. And I want to apply this in this setting and ask for so-called corresponding spaces. So there's an operator space, there's a corresponding function space. The question is, what is it? And unfortunately, I don't know the answer, only in one case. So an easier task is to look at commutative subalgebras of the resolvent algebra. Then we have Gelfand theory and more tools, and we can actually answer the question. And what is more ongoing is to do the whole thing for representations of the resolvent algebra where the underlying symplectic space, I will explain this in a minute, is not finite dimensional, but for example, infinite dimensional, a separable Hilbert space, for example. And then, yeah, we can try to generalize or adapt the methods. But then tools are missing, in particular, this QHA, quantum harmonic analysis, not available in this case. Okay, so this is my plan. I hope I can go through this. And let me start very simple. So we consider a symplectic vector space. So this is a real vector space X, and sigma is a symplectic form. And in our example, X will be Cn, considered as a real vector space, or if you want, the cotangent bundle of Rn. H is a Hilbert space, which is, for example, complex Hilbert space separable, and it will be Fock space later on. And then we consider a real linear map from the symplectic space into essentially self-adjoint operators on the Hilbert space. So here D is the domain, and that should be a core for all elements in the image of phi. So if you consider phi of f, let's say, on this core, and you look at the yeah, okay, then it did. So in particular, this is a dense space, and it should be also yeah, it is a core dense and invariant. And then I assume that these maps fulfill the canonical commutation relations. So if you look at the commutator phi of f and phi of g on this domain D, since it's invariant under the operators, we have no problem defining the product. Then this is I times the symplectic form times the identity. And also we are dealing with the self-adjoint operators, so we have phi of f equal phi of f star on D. And these are the canonical commutation relation, and I guess you all have seen them many times. And
wait a minute. Symplectic form applies to two elements from X. So
yes, yes.
F and G just elements from F.
Yeah, these are not functions, even though they look like functions. But these are elements exactly. from the symplectic space.
Yes, just element of X.
Yes, element of X. So phi is defined on X. X will be Cn later on. So complex vectors in Cn if you want. So if this symplectic space is non-degenerate, then we cannot have a representation of the CCR inside bounded operators. So naturally, we have to deal with unbounded operators here in this case. And now dealing with unbounded operators is not very pleasant sometimes, because you always have to be aware of the domains and so on. You cannot easily multiply them. So one strategy is to find a C-star algebra of bounded operators which encode the CCR. And the idea is to, based on the essentially self-adjoint, is to take these unbounded operators and form functions of those which then are bounded operators. And then we take these functions and we look at the generated CCR algebra and generated C-star algebra. And we think of this algebra as an algebra that generates the canonical commutation relation. And the very classical way to do this goes back to Hermann Weyl. And what he does is he considers exponentials of these self-adjoint operators. So he considers x of I phi of f. And now these are unitary operators, of course, where f again runs through the symplectic space. And then one can look at the C-star algebra, which is generated by those operators. And this is denoted here by delta x sigma. So we keep the notation of the symplectic space. This is called the Weyl algebra or CCR algebra.
Wait a minute, Wolfram, you mean that doing this algebra, you consider bunch of bounded function phi?
Yeah, so phi of f is this, so phi of f are these operators.
Yes,
right?
yes. But to build algebra, you need to have different operators, so phi can change.
Yeah. No, phi is fixed. Phi is fixed. F changes.
Phi is fixed.
Phi is fixed, yeah. So let me go back. You have these phi from x to self-adjoint operators. So you can look at phi of f. F, of course, the argument changes. You get a lot of operators, and then you form from them unitary operators by putting them in the exponential with an I, and then you get a bunch of operators, and these generate a C-star algebra. This is the Weyl algebra. These are all unitary operators.
Okay.
And some things are known about this algebra. For example, it's a simple algebra. So the only closed ideals inside are the trivial ideals. And you can do this a bit more abstractly if you don't have a Hilbert space. There you can define the Weyl algebra just by relations. So you look at the set of unitaries, which is here denoted by delta f, where f runs through the symplectic space. And then you have a certain relation. So df star is d minus f, and you have this well-known Weyl form of the CCR, which comes, of course, from this exponential if you plug in the CCR of the arguments here. So you can do it this way. And here's a second approach, which also takes this map phi, the canonical relations, and produces from these unbounded operators bounded operators, but now we do not use the exponential, we use the resolvent. And that's more recent approach, and I think it's around 2008 when they proposed this. So they look at resolvents of phi of f. So phi of f is a self-adjoint operator. So if you consider I lambda, where lambda is real but should not be zero, then that's invertible, and you look at the resolvent. And that now gives you a bounded operator. And then you take all these bounded operators where f runs through x, and you generate a unital C-star algebra by this. And this algebra is now denoted by R, and it's called the resolvent algebra. So what I want to do here is I want to look at this resolvent algebra not in a very abstract setting, but in the setting of Toeplitz operators on the Fock space, where we have a very explicit representation of the resolvent algebra. And then I want to ask a few questions which are also related to Toeplitz algebras and then Toeplitz operators, as you will see. Nevertheless, you can really also study the resolvent algebra abstractly, without having a Hilbert space there, as an algebra which is defined by generators and certain relations. And here are the relations which we need. So we consider a universal unital star algebra, which is generated by a certain set of elements which are denoted by R lambda f. So this, of course, in concrete representations are resolvents, where lambda goes from R minus 0 and f runs through the symplectic space. And now we need a lot of relations which reflect the fact that R lambda f should be resolvents, and also that this map phi from the symplectic space to the operators, the self-adjoint operators, that this is a linear map, And we need also relations that reflect the fact that these fulfill the CCR. And I give you now these relations. So if we take parameters lambda, mu, and nu in the reals without 0, and two elements f and x from the symplectic space, then the first relation says that r lambda of 0 is minus I divided by lambda 1. And this really reflects the fact that phi is linear, so it maps 0 to 0. Right? So if you think of a resolvent where the operator is 0, then you get just the right-hand side. The next one, of course, reflects the fact that these operators phi of f, they're self-adjoint, right? Then that's what happens if you take a star of the resolvent, you get a minus sign here in the first argument. So this should be thought as I lambda minus phi of f to the minus 1. So from the I you get the minus. So here are some more things. Nu of r, nu lambda, nu f should be r lambda f. So this reflects the fact that we are dealing with an R linear map. And again, if you think of this as a resolvent, that's an equation which is completely clear. And then 4 says that we're actually dealing with resolvents, and that comes in form of the resolvent equation. That's the relation we want. And there's one more. There are two more. 5 is this equation. So this looks a bit strange. If you look at the commutator of two resolvents, this is I times the symplectic form of f and g. So these are elements from the symplectic space. And then this product here of resolvents. And if you work it out a bit, if you play around with resolvents of operators phi of f, which themselves fulfill the CCR, then you see that this relation somehow reflects a CCR of phi of f.
Excuse me, Professor.
Yes.
I read that the Weil algebra can be seen as a unitary group of, well, it can be represented for each t. Is this lambda the equivalent to the t that can be seen in the Weil
algebra?
Yeah.
Yeah, in a sense, so this lambda really is some parameter which later on can be also complex, and in a sense it plays that role also because of these kind of relations 3 here in the linearity. But it's yeah, it's a parameter which plays a similar role maybe than t.
I'm not sure that exactly the same role, because in Weil algebra, changing t involves some group properties, which is not the case for resolvent algebra.
Yeah, it's a different. It doesn't behave like the t. It's a parameter, like the t is a parameter, but yes, there's no direct relation, I would say. Yeah. But of course we need the lambda, otherwise we cannot invert, right? So the operator phi, the phi of f is not invertible in general. So we really have to put a non-real parameter there. Okay, and then there is the last relation, which is 6 here. This also looks complicated, but it's nothing mysterious. It reflects just the additivity of phi. So if you use this in the resolvents and you calculate the left-hand side, then you see that the right-hand side comes out. So that should also be one of the relations. Okay,
I'm sorry, Wolfram. I'm sorry.
Yes.
One question about the axioms. In the axiom 4, you have the difference of the resolvents with the same f and different lambda and mu.
Yes.
But there is another resolvent equation for the same number lambda and two different operators. So you don't.
So I only use this. I think all the other relations can be obtained from these.
Okay, thank you.
So this, of course, there are more relations, but you need to have somehow independent ones.
Yeah, the difference of the resolvent with the same lambda and two different operators, maybe it would be simpler than 5 and 6. Well, I don't know.
Yeah, you should get it maybe from a combination of 5. and 6 probably somehow. But don't worry too much about these abstract relations. In the end, we will deal with true resolvents anyway.
Maybe
so this is,
it would be, it could substitute 6. I don't know.
Yeah. So I'm not saying these are the only ways to encode this, but these are at least independent relations from which you can get others.
Thank you.
Okay, so then resolvent algebra is then defined as the closure of this, and we still have to produce a norm. With respect, we can take the closure or the completion, and such a norm can be obtained through the GNS construction. But I don't need this here very much because I will only work on a very explicit representation of the resolvent algebra. Nevertheless, you can do it for any symplectic vector space, whether or not this is finite dimensional. Okay, so now we have these two objects. We have the Weil algebra and we have the resolvent algebra, and the question is why do we need two? Why isn't one enough? And here are some properties again of the Weil algebra. So this was my notation. So first of all, if you look at the generators of the Weil algebras, which were these exponentials, e to the I phi f, then, for example, we have this norm equality, so that they have all distance from the identity if f is not 0 equal 2. And you can use this to show that this algebra is actually non-separable. It's non-separable algebra. Also, I mentioned it's a simple algebra. So these are two properties which always hold. And here are a few properties of the resolvent algebra, which with respect to which they are different from the Weil algebras. So here's one notation. So assume we have a self-adjoint operator on a Hilbert space. Let's call it A. And we have C star subalgebra C of the bounded operators on H the Hilbert space. And then here's the definition. So this operator A, this might be unbounded operator, but we call A affiliated to that algebra if the resolvent of this operator, which then is a bounded operator, is actually inside the algebra for some parameter lambda in R. And then there's another notion of a mollifier. So we call an element M in this C star algebra, which is invertible on its range, a mollifier if of an given element A, if of this operator A here, if the product AM and the closure of MA, if these are bounded operators, and not only bounded operators, if they are even elements in the C star algebra. And these are somehow related. So assume that A is affiliated to the C star algebra, which means that this resolvent here, I lambda minus A to the minus 1, is in the C star algebra. Then we can look at the product A from the left and A from the right, and we take the closure. And if you calculate it, you get the right-hand side. So I lambda times I lambda minus A to the minus 1 minus the identity. And if A is affiliated to C, then the resolvent which appears on the right-hand side is in C, so the whole thing is in C. In other words, this resolvent A is actually a mollifier of A itself. So whenever A is affiliated to the C star algebra C, then the resolvent I lambda minus A to the minus 1 is a mollifier. And so this somehow is related to the construction of the resolvent algebra. So the resolvent algebra, if you think of this as an algebra in a concrete representation, so on a concrete Hilbert space, then it is just generated by resolvents of these operators phi of f. So it's the C star algebra generated by these resolvents. And so by definition, each operator phi of f, which is a self-adjoint operator, is affiliated to R because the resolvent is, of course, in R. And that means each element phi of f contains a mollifier, which is the resolvent corresponding to itself for some parameter lambda. So there are a lot of mollifiers in the resolvent algebra. On the other hand, in the Weil algebra situation is completely opposite. So here one can show this is a theorem by Buchholz and Grundlik. So these were the guys who introduced who introduced the resolvent algebra, that in the Weil algebra, it contains no non-zero element m such that phi of f times m is bounded for some f, not even bounded. And so it can certainly also not be in the Weil algebra itself. So in other words, the Weil algebra contains no modifiers of any non-zero element inside. And in particular, phi of f is not affiliated with the Weil algebra, because if it was, then a resolvent of phi of f would be a modifier, as we just saw. So it's a completely opposite situation here. So here's some other properties which make the resolvent algebra more suitable for physics. So the Weil algebra is a simple algebra. So it does not contain non-trivial closed ideals. However, the resolvent algebra has an interesting and non-trivial ideal structure. And here's an easy example of this. So for example, if you take lambda in R without zero and f in the symplectic space without zero, then you can look at the closed two-sided ideal, which is generated by this fixed resolvent R of lambda f. And that's a proper ideal in the resolvent algebra. And so, but there are many, many more ideals. Some are related to subspaces of X. And so the resolvent algebra, different from the Weil algebra, is not simple. And it's also non-separable, like the Weil algebra is. And if X is finite dimensional, and we will deal with this case later on in the Fock Bargmann representation, then the resolvent algebra contains, for example, all compact operators on the Hilbert space. Okay, so as I said, physicists, or some of them at least, seem to like the resolvent algebras for some reason. So here's one of this. Here's another negative result about the Weil algebra. So they observed that the Weil algebra, at least in concrete representation, does not allow time evolutions or very general time evolutions. And by this, they mean the following. So here I want to only look at the simple case where the symplectic vector space is R2. So if you want the cotangent space of R, and I identify it with C, and I take a standard symplectic structure. And then we can, for example, look at the Schrödinger representation, which maps the corresponding Weil algebra into the bounded operators on L2 space over R2. And now we can take a Hamiltonian, so which is of the form minus Laplace operator plus some potential. Potential here should be L infinity intersected L1 on R. So R2 is, so to say, the phase space. Okay, P doesn't appear here, forget about this, and Q are just the coordinates, and V of Q is a real valued potential, and this is self-adjoint operator. And then one passes to e to the minus it of h of this Hamiltonian, and the dynamic somehow comes from conjugation by these operators. Maybe there, on the other hand, this minus should be a plus. Mm-hmm. And then it is known that in this representation, in the Schrödinger representation, in this explicit example of R2, this is only invariant under this dynamics, so under conjugation of this operator in the trivial case, namely with the potential 0. Otherwise, it is never invariant. And so physicists want to have this actually invariant for non-trivial potentials. On the other hand, with the same notation, the resolvent algebra behaves a lot nicer. So here, the following is known, at least. Okay, I don't know whether it's the sharpest result, but if you take a potential which vanishes, continues vanishing at infinity, it's a real valued function, so that you get self-adjoint operators. And you look at the Hamiltonian here again, and then that actually induces a dynamic on the resolvent algebra. So this algebra actually is invariant under conjugate. Again, here's a minus sign. This should be plus. So this is invariant under conjugation, under the dynamics which is produced by this Hamiltonian. So here's another thing. Maybe this is almost the last general result I want to tell you before we pass to the Toeplitz operators, which says that this Hamiltonian here, again, where V is a continuous function vanishing at infinity, real valued, is actually affiliated with the resolvent algebra. And this means that again, the resolvent, we look at the resolvent of the Hamiltonian here, actually is in the Schrödinger representation of the resolvent algebra. And this is true for all lambda. So these are some good properties of the resolvent algebra, which in general the Weil algebra does not have, but only maybe in the trivial cases where the potential is vanishing and we only have the free Hamiltonian, so to say. Okay, so now let me get a bit more concrete, and I want to look at the Fock Bargmann representation of CCR and at the resolvent algebra and the Weil algebra. What can we say about this? So now I look at Cn, complex n space, and I equip it with the standard symplectic form. So I take the imaginary part of the Euclidean inner product between W and Z. So these are two n vectors. And then, as usually, I fix a Gaussian measure on Cn, which is denoted by d mu. So it's a probability measure with the Gaussian kernel here, and dV is just the Lebesgue measure. And then we all know the Fock Bargmann space or Siegel-Bargmann space, which consists of Gaussian square integrable entire functions, and my notation is F2 here. And we have the orthogonal projection, of course, from the L2 space. Maybe this C2 should be Cn of Gaussian square integrable functions to the Fock Bargmann space. And as we all know, this is a reproducing kernel Hilbert space, and we can write the reproducing kernel explicitly. It's just this exponential with the Euclidean inner product between Z and W. And then we have Toeplitz operators, which are compressions of the multiplication operators. So P times MF, MF is the multiplication by F. And Toeplitz operators here are usually operators with unbounded symbols. So they could be unbounded, and mostly they are real valued, but not all the time. Okay, so this is our usual setting. And then we have the unitary Weil operators on the Fock space. And let me also recall this. So we look at the normalized reproducing kernel, and then we look at the shift operators by some element W in Cn. And the shifts, of course, are not unitary. The Gaussian measure is not shift invariant, but if we multiply by the normalized reproducing kernel, then this gives an operator WZ, which actually is a unitary operator.
And don't your W should be Z?
Yes, thank you. Okay, there's another typo. This W must be set, yes. And okay, so then these are unitary operators. If I take a star, that means I replace Z by minus Z, and they fulfill the Weil relations, which are written in the second line here. So we have a concrete representation of the Weil algebra in the bounded operators on the Fock space. And so we just take these unitary Weil operators where Z runs through our symplectic space, and we look at the C-star algebra generated by this. And this is CCR Cn with respect to the standard symplectic form. And so there are no Toeplitz operators for the moment. So the question is there some relation to Toeplitz operators? And in this setting, the answer is, of course, yes. And here we can look at the following assignment. So we take the symplectic form. This, of course, is a polynomial. We fix the second component. That's, of course, a linear function. It's unbounded on C. But we can look at the Toeplitz operator with this unbounded symbol. It's also real valued. And that really gives an assignment from the symplectic space to essentially self-adjoint operators on the Fock space, and they fulfill by a direct calculation the canonical commutation relation. And you can do this on some core D, which I do not want to specify here. What is okay, this follows, of course, by direct calculation. What is more specific here is maybe that the Weil operators, WZ, that they are actually also Toeplitz operators, and not even not just this, there are even Toeplitz operators with bounded symbols. So if you take now the exponential e to the it sigma, then this is the Weil operator, W set. But this itself is a Toeplitz operator with a certain symbol, G of Z, which can be calculated. So it's this kind of G index Z is this kind of exponential or trigonometric polynomial, if you want. So what we see from this is that the Weil algebra in this standard setting, which is the C-star algebra generated by the Weil operators, is actually inside the full Toeplitz algebra, because the generators of the Weil algebra are actually Toeplitz operators with a very, very simple, so to say, bounded symbols. So the Weil algebra is inside the Toeplitz algebra. And one can say more about this. And here's an old result by Coburn, which says that actually the CCR CN can be actually identified with the linear closure of Toeplitz operators with symbols phi, where phi comes from the space of trigonometric polynomials. So trigonometric polynomials are just polynomials in these exponentials. So the linear span of these maps W go to x of I sigma W set, where set runs through all Cn. So this is maybe, if you look at this, not immediately clear that the linear closure actually is a C-star algebra, but this happens here. As you know, also it happens in many other cases. But there are some questions now. If we go from the CCR algebra to the resolvent algebra in this Fock Bargmann representation, then the first question is this also a sub-algebra of the full Toeplitz algebra? Can we find it there? And a bit more refined question is whether the resolvent algebra is a Toeplitz algebra itself, as CCR is. In other words, whether we can find a space of symbols, bounded symbols, such that the resolvent algebra in this setting actually is the C-star algebra, which is generated by Toeplitz operators where the symbols come from this space. And of course, one wants to know what is that space S. And what is clear is if you take these Toeplitz operators TF, which fulfill the CCR with the unbounded symbols, and then you pass to the resolvent of this, then of course the resolvents of Toeplitz operators are not Toeplitz operators in general, but they might be in the C-star algebra generated by some Toeplitz operators. So the first question is rather easy to answer. The first question was whether the resolvent algebra in this representation is actually in the full Toeplitz algebra. The answer is yes, and that's not so hard to see. So here's the argument. If you take set in Cn and we look at this group of this one parameter group of unitary operators, so WSZ are the Weil operators, that strongly continues. And of course, the generator is just I times the Toeplitz operator with the symbol 2 sigma of Z. So we can actually write the resolvent of this generator here, which fulfills the canonical relations through the Laplace transform as an integral from 0 to infinity of this unitary group, this strongly continuous one parameter group which generates it. And now, since we know that in the Fock Bargmann representation, these Weil operators are actually Toeplitz operators, where the symbol are nice bounded functions, such that actually this integral here converges in a uniform way, at least if this lambda here, this parameter is positive. And then we know we really have an integration over a family of Toeplitz operators with bounded symbols, which then tells us that the resolvent also is in the full Toeplitz algebra. And you get a similar formula in the case where lambda is negative. Then you have to somehow switch the path of integration a bit so that you also see that you have an integral representation of the resolvent which converges in the nice way. So you see that the resolvent algebra actually is a sub-algebra of the full Toeplitz algebra. The second question, whether the resolvent algebra actually is a Toeplitz algebra, this is a bit more difficult to answer. And actually, I know the answer, but it's not so clear what the symbol space is in the most general setting. And to analyze this question, it is useful to use quantum harmonic analysis. And here I want to also only recall one result from this theory, which is adapted to the setting of Toeplitz operators. And quantum harmonic analysis was introduced by Reinhard Werner from Hannover here, and then in the setting of Toeplitz operators, it was studied by Robert Fulsche from Hannover. And what one does here, so one aspect of quantum harmonic analysis is correspondence theory. So one tries to find a relation between certain subspaces of the bounded uniformly continuous functions on Cn and certain subspaces of an algebra T, which turns out to be the Toeplitz algebra, inside bounded operators on the Fock space. And so these kind of spaces, I will explain or recall what relation means, are then called corresponding spaces. And so to explain this, I have to recall the notion of a shift. So if you have a bounded uniformly continuous function, f, and a bounded operator, then we can shift those elements or those objects in direction z of the complex n space. And shifting a function just means shifting in the argument. So f goes to f of dot minus z, and shifting an operator means I have to conjugate this operator by the while operators wz. And now the bounded operators, the bounded uniformly continuous functions are actually L-infinity function, which behave nicely under these shifts in the sense that the map which assigns z to the shift alpha z is continuous with respect to the L-infinity norm. These are just bounded uniformly continuous functions. And then there's another algebra C, which are bounded operators on the Fock space, such that alpha z actually also is continuous with respect to the operator topology. And that's somehow a strong condition. And now, if we take a subspace, or later on sometimes subalgebra.
Wait a minute, Wolfram.
Yes.
So, well, so C you define as you pick up all operator A from bounded and Fock space, so that this mapping is continuous.
Yes, with respect to the operator norm.
With respect to
not just strongly continuous.
Yes, it's not all operators, it's just you pick with this property.
Yes, yes. So I only take those operators which behave in that way under the shift, and not all of operators are of this type.
In the same story, in the line above, you pick only those F such that this map is continuous.
Yeah, and these are precisely, this can be precisely described as the space of bounded uniformly continuous functions.
Mm-hmm.
And in the second line, this C also can be described.
Okay.
So we have this. So C, of course, is an algebra. It's not just a linear space. And also, okay, BUC also is a C-star algebra. C is also a C-star algebra inside L of F2. And now we can also consider subspaces of the bounded uniformly continuous functions, which are shift invariant or alpha invariant. And that just means the shifts leave this algebra or this subspace invariant for any set in C, and C should be actually Cn here. And the same for operators. So conjugation by W set should leave this, this invariant. So these are alpha invariant spaces. Okay, and now to formulate the correspondence theory, we have to also recall the Bayesian transform. So if I have a bounded operator on the Fock space, then the Bayesian transform is a function, a twiddle, which is defined through the normalized reproducing kernel in the usual way. So I think you all know this. And here's the correspondence theory in the version which was then proved by Robert Fulsche. And it says, if you take a subspace, just a linear space, inside this C-star algebra C, which I have just defined. And if this space is closed and invariant under these shifts, then there is a unique shift invariant closed subspace in the bounded uniformly continuous function. This is called D0, with the property that this space D1 is the linear span of Toeplitz operators with a symbol come from D0, not an algebra, linear span. And if you take an operator A from this C star algebra C, then you can somehow, then the following are equivalent. You can somehow detect when this operator actually lies in D1. So A is in D1 precisely, or if and only if, its Bayesian transform ends up to be in D0. And D0 also can be described, the corresponding space. This is the closure of Bayesian transforms where, of operators which come from D1. And so these two spaces which exist and are uniquely defined by each other are called corresponding spaces. So if you have D1, there's a corresponding D0. If you have D0, there's a corresponding D1. And important is alpha shift invariant. Okay, and now I want to recall what is actually this algebra C. Maybe I should go back to the definition. So this was C here, all bounded operators, such that the assignment set goes to alpha set, so the shifted operators. This gives you a continuous map with respect to the operator norm. And the result is that this actually precisely is the Toeplitz algebra, the full Toeplitz algebra. And then also by a result of Qingbo-Shah, it is known that that full Toeplitz algebra is actually a linear closure of Toeplitz operators with symbol in L infinity, not the C star closure. It's not only the C star closure, but also the linear closure. So it's smaller than you maybe would expect.
Wolfram, what is a part of full shape? What is a part of Shah in this theorem?
Yeah, in a sense, all of this is that this equality of C and T, in a sense, comes from Folch's result, and the fact that the linear norm closure is the C star closure is Shah's result.
Okay.
But the whole thing also follows from the correspondence theorem very easily in 2 or 3 lines, Shah's result in the case of the Fock space. But Shah proves this actually for Bergmann spaces, and in the end he says Fock space works similarly. And in Bergmann space, we don't have the correspondence theory. Okay, so the next observation is that this resolvence of Toeplitz operators, which we have just considered, actually behaves nice under shifts. So if you take a resolvent of a Toeplitz operator, so R lambda set is actually this resolvent above here, and you shift it along some vector W in Cn, then again you get a resolvent, and that shift only touches lambda, but it moves it to purely complex direction. And the next observation is this one. The resolvent algebra in this setting is generated by resolvents of Toeplitz operators, where this lambda is real but not 0, and that runs the whole Cn. But also these resolvents actually exist for lambda in complex plane, but not a multiple, a complex, a pure imaginary multiple of R. So if you allow these lambdas in this larger space, C without IR, then you get the same algebra. It doesn't increase. It's the same thing. So this shift here in pure imaginary direction really gives you, again, an element in the resolvent algebra. In other words, the resolvent algebra is shift invariant. So it falls under this theory. So the resolvent algebra is, of course, closed. It's a C-star algebra. It's a shift invariant subalgebra of the full Toeplitz algebra. So quantum harmonic analysis is a good theory to study this. So then the correspondence theorem tells you the following. Automatically, it tells you that the resolvent algebra actually is a Toeplitz algebra. That means there is a space, which is the corresponding space to the resolvent algebra of symbols, such that the resolvent algebra is the linear space, the linear span of Toeplitz algebra, of Toeplitz operators, where F comes from this space D0. And also one can prove that this linear span actually coincides with the C-star closure. So it's it's automatically a C-star algebra because the resolvent algebra is a C-star algebra. And what we also know is that this symbol space D0, it lies inside the space of bounded uniformly continuous functions. It's itself alpha, so shift invariant, and it is closed. But we don't know what it is. So the question is, can we find it? What is D0?
Do you have any guess about that?
I will tell you. I will tell you. So the question is, we know it exists, and we could also somehow write it down. It comes from Bayesian transforms of resolvents, but of course, it's not unique. Okay, this is unique, but it's not so clear what it really is. So I will tell you. So in many examples, the corresponding spaces between operators and functions is really what you believe, what you think it should be. So if you, for example, look at compact operators on the Fock space, that's also shift invariant closed subalgebra of the bounded operators, then the corresponding space to this are just continuous functions vanishing at infinity. If you take the Weil algebra in the Fock Bargmann representation, this is also shift invariant algebra. It has a corresponding space, and these are almost periodic functions. These are the C-star closure of the trigonometric polynomials. And if you take the resolvent algebra, we don't know what is the corresponding space. And naive guess is the corresponding space really is just the C-star algebra, which is generated by the resolvent functions. So you take the symplectic form and you form these resolvent, these are just functions now. And you take the inverses, so 1 over, where lambda is in C without IR, and Z runs through Cn. And then you look at the C-star algebra generated by those functions. And this is what we call classical resolvent functions. And if you look at all these correspondence above, then maybe the good guess is the classical resolvent function should be the corresponding space, right? So that has good properties. Of course, it's closed since we define it as a C-star algebra of something. And it's also contained in BUC, bounded uniformly continuous functions. It's also shift invariant under the usual shift of functions. That's easy to see. And it has more invariance. It's also invariant under the parity operator, which maps f to f of minus the argument. So it is a good candidate. And the other thing is that if you now look at Toeplitz operators, where the symbols are in this resolvent, in the C-star algebra generated by resolvent functions, then that also coincides with the linear closure of Toeplitz operators, where symbols are from the resolvent functions. So the C-star closure is the linear closure. That's also true. So if we want to prove that that corresponding space D0 corresponding to the resolvent algebra actually is the algebra of the classical resolvent functions, then we only have to prove that, or we have to prove that the resolvent algebra is the C-star algebra, which is generated by Toeplitz operators with symbols coming from the classical resolvent algebra, not the linear closure, but the C-star algebra. We could a priori look at the larger space. And that uses, so this equality of C-star algebra and linear closure that is based on a more general theorem, which also is in one of the papers by Robert Fulsche. And it uses the invariance under another parameter, but I do not want to explain these details here. And here just a few small other remarks. So the continuous functions vanishing at infinity, they are actually inside the C-star algebra generated by classical resolvents. And the compact operators are inside the resolvent algebra. So somehow we may expect that this correspondence extends the one between C0 and K. Okay, one inclusion we can prove. So what one can see is that the resolvent algebra is inside the C-star algebra generated by Toeplitz operators, where the symbols come from the classical resolvent functions. And also the proof is based on correspondence theory. So here are some ingredients. I cannot give the whole calculation. So now you have to start to do calculations actually. So the first observation is this one. If you look at the classical resolvent function and you look at the C-star algebra generated by this, even so it's not so clear what it is clear that it's invariant under the Bayesian transform. And the next observation is we can actually explicitly get integral transforms or integral representation of the Bayesian transforms of products of classical resolvent functions, somehow based on the Laplace transform. And on the other hand, we can also look at products of resolvent operators. And these, and we calculate the Bayesian transform of those. And then the question is, can we somehow approximate one Bayesian transforms by the others? And they look rather similar, except for the resolvent operators, it's more complicated. But one can see.
May I ask you a question? Wolfram?
Yes.
So regarding your proposition, so resolvent algebra is inside of C star with symbols from your classical set. This is
Yes.
inside of C star algebra with all infinity symbols,
Yes.
which coincides with the resolvent algebra.
No. Not the full Toeplitz algebra coincides with the resolvent algebra.
Resolvent just inside the full.
Yeah, this is a lot smaller. Right.
What is the full and Shah results?
Shah result says that the C-star algebra, which is generated by Toeplitz operators with bounded symbol, coincide with the linear closure.
Yes, linear. And Fulcher part?
So Fulcher part says that the same is true if you replace all L infinity symbols by just symbols from the classical resolvent functions.
Okay.
You take another symbol space, which is a lot smaller.
Okay.
So what we have to do is we have to take resolvents, so operators, and finite products of those, and we calculate the Berezin transform. That gives a function. And our task is to now take Berezin transform of resolvent functions and try to approximate Berezin transforms of resolvent operators by resolvent functions. And that can be done by direct calculation and using invariance under the Berezin transform of this R class. And then we show that Berezin transforms of resolvents, of resolvent operators, are actually in the C-star algebra generated by classical resolvent functions. And then the correspondence theorem tells you actually this inclusion. The resolvent algebra is inside this C-star algebra. So this last, second last line together with the correspondence theorems gives you the result. So the question is, do we actually have equality up there? Are these C-star algebras the same or not? And if the dimension of the space is bigger than 1, not 0, if the dimension of the space is bigger than 1, then it is very difficult to do the approximation the other way around, because that's what we should do. So it's very difficult to uniformly approximate Berezin transform of products of resolvent functions by Berezin transform of product of resolvent operators. That's complicated, and we don't know how to do it or whether we can do it. So in other words, if the dimension of the space is bigger than 1, then we do not know whether the resolvent algebra really is the C-star algebra generated by Toeplitz operators with symbols in the classical resolvent algebra or resolvent functions. So I want to discuss a simplified task. And instead of considering the full resolvent algebra, I want to consider commutative subalgebras of this. And there are many, which are induced from Lagrangian subspaces of Cn. And then we are in the setting of commutative C-star algebra, and we have more tools. We have Gelfand transform, Gelfand theory, and that can really help to analyze the structure of the resolvent algebra. I mean, of these commutative subalgebras. And let me just recall some definitions. So we look at the real subspace of Cn, of real dimension n, and we call it Lagrangian if the symplectic form vanishes on that space. So sigma of Z and W is 0 for all Z and W in that real subspace. So for example, if you take V equal Rn in Cn, then of course that's a Lagrangian subspace because that imaginary part of Z times W vanishes, right? Everything is real. So if we have a Lagrangian subspace, then we can always decompose Cn as this space direct product with the complementary Lagrangian subspace, which just appears here by multiplying with I. And now we do not form the resolvent algebra with respect to the complete space Cn, but just with respect to that real subspace. And that algebra is then denoted by Rv. So we do the same thing. We look at resolvents R lambda Z, but now Z does not run through whole Cn, but only through this Lagrangian subspace V. And that, of course, gives you a subalgebra of the resolvent algebra, right? We have less generators. And now the point is, if you take such a Lagrangian subspace and you look at this corresponding algebra, then it's commutative. It's a commutative C-star algebra. It's a subalgebra of the full Toeplitz algebra, and it's still shift invariant. And the reason comes from one of these relations, which I showed you in the beginning, namely relation 5. And it tells you if you take a commutator between two resolvents here, then it's a multiple of the symplectic form times some operators. But if you have a Lagrangian subspace and f and g are from the subspace, then by definition, the symplectic form vanishes, right? So these commute, and you get a commutative algebra. And also, once again, shifts only affect lambda, and you get somehow, and do not affect f and g here. So it's shift invariant.
Wolfram,
So we can.
question. And there is no spaces bigger than Lagrangian containing Lagrangian that produce commutative sister algebra.
Not obviously, no. I think this argument only, this is somehow maximal. You can take smaller ones, I guess, but this
smaller, I
maybe
mean
is
that
maximal.
contain
It's maximal,
Lagrangian,
yeah.
so bigger.
Yeah, yeah. So if you want to have commuting, then you really need the forms, the symplectic form to vanish, right? Because you have equality here. Okay, so we look at the smaller space, the smaller algebra, which I call, okay, sorry. So this is the resolvent algebra RV, and there's a corresponding resolvent function algebra, so which is the C-star algebra generated by resolvent functions, where the set only comes from this space V. Okay, this is just the same thing, except that we replace Cn by V. And now we can ask the same question again, whether this resolvent algebra and these resolvent functions are actually corresponding. Corresponding in the sense of what's written in the last line. So, and again, the same result by Fulcher tells you that the linear space of Toeplitz operators with a symbol come from this classical resolvent algebra corresponding to the Lagrangian space actually coincides with the C-star closure. So these are the same things. We really can try to prove the weaker statement where we replace the linear span of Toeplitz operators by the C-star algebra. That's a priori looks like a bigger space, even though it's the same. And then we're dealing now with commutative algebra, so we can look at the Gelfand spectrum of an algebra, which I denote by M of A. So this is just a notation. And then the observation is that if I have a Lagrangian subspace and I look at the operator algebra, resolvent algebra, and the function C-star algebra generated by classical resolvents, then that has the same, they have the same Gelfand spectrum. And this is actually some compactification of this Lagrangian subspace, which can be described in a very precise way. So I do not describe it here, there's no time, but one can actually really describe this.
But any hint about that?
Pardon?
Any hint about that?
Yeah, you have to somehow compactify some Krasmannian. So yeah, it's by some condition. So it's not easy to say in 3 words.
Okay.
But if you're interested, there's actually a paper. This is nothing we did. There's a paper on this. I can send you, and it's the whole paper describes the compactification and some properties of this. Yeah. So anyway, you can use this fact to show that they are actually corresponding because they're the same as the C-star algebra. And this gives actually an answer to our question in the one-dimensional space. So if the symplectic space is just a complex plane, and then the question, so then there's just there are not so many subspaces, and the situation is geometrically easier. There's just one way, so to say, to go to infinity, and then actually one can prove that the classical resolvent function correspond to the resolvent algebra. This is clear. But as soon as the dimension is bigger than 1, it is not clear, and I actually started to doubt that that's really the corresponding space. But I have no evidence that is not the case. Okay, maybe my time is up. Let me just say a few words about the extensions. If you still give me 2 minutes. So what we try to do now is to understand the whole setting in an infinite dimensional setting. So I want to replace Cn by a separable complex Hilbert space. And I take the same symplectic form, which is imaginary part of the inner product. And now I want to consider a Fock space representation. So infinite dimensional Hilbert space has, of course, no shift invariant measure, but it still has a Gaussian measure. And the construction is maybe the easiest construction is this. Take a sequence of non-negative integers. So this t should be tk, which is also summable. And then we can consider 3 Hilbert spaces. The first one is just L2 sequence space. Second one is H1/2, where the summation is somehow weighted by 1 over Tn. And then H1 is the one where the summation is weighted by 1 over Tn squared. So these spaces from the conditions on T, they are inside each other. And the embeddings are, so with the corresponding norms, of course, are Hilbert-Schmidt. And now what you can do is the following. I look at the space in the middle, which is H1/2, and I can consider this as a symplectic Hilbert space with a symplectic form which comes from the natural inner product on this, standard inner product. But still we have to weight it by Tn. And then we consider C infinity, which is just the infinite product of C. And on C infinity, we consider a product measure, infinite product of measures, where on each complex line, we have a Gaussian measure, but they're not the same. They have a different tk here in the denominator. And now the thing is, if you consider this infinite measure, this measure on this infinite space, C infinity, and you restrict it to L2 space, which sits inside, then this is a linear space, and the measure could be only 1 or 0. And from the L1 property of the sequence tk, one can show that actually this is a space of measure 1. L2n is a space of measure 1 inside C infinity. So we can restrict the measure to L2, and that's the Gaussian measure. It's a Gaussian measure on H. And now we can do the same thing as before. We have Toeplitz operators. We can represent CCR on H1/2. We have the canonical relations, and we can look at the resolvent algebra, and it's also inside the full Toeplitz algebra. That's also easy to see. We can, for the moment, we cannot go further because we don't have quantum harmonic analysis in this setting. So, but it would be interesting to prove a correspondence theorem and to introduce quantum harmonic analysis in this infinite dimensional setting. But there's a lot of obstruction which come from the infinite dimensional measure theory. In particular, there's no L1 space because there's no Lebesgue measure. So one has to really think about this, and then that's some part of some ongoing project with Miguel Rodriguez, and we hope to have some progress there. Okay, so I think I'm already over time. Here's some references. The first one gives the details on what I just explained. It's on arXiv with Robert Fulsche. And the second one has a lot of information on the resolvent algebra in an abstract setting. Yeah, thanks. That's all. Thank you for your attention.
Thank you, Wolfram. Very, very interesting question. You know, all the time we are looking at the full Toeplitz algebra. All the time we can find very different their description. And this fascinating thing, I think, for Toeplitz algebra.
Yes. So it's algebras generated by resolvents. I'm not sure whether they're very much studied.
Yeah.
But there are many related questions. So, for example, to extend this from the symplectic vector space to the symplectic manifold, and I think there's a way to do this.
Very, very naive question. Why do you choose sigma for symplectic form? It's normally omega.
I think this is the notation from the Buchholz-Grundling paper, which I kept.
Raoul can ensure that normally it's omega symplectic form. Yes, Raoul?
Yes, I guess so, but yeah, I got that, but it's okay, of course.
No, of course, okay, but well, somehow we're accustomed to omega for symplectic form. But never mind.
It comes from the physics community. Maybe they like sigma. I don't know.
I see. Because sigma normally is kind of measure or whatever.
Yeah.
In mathematical mind, sigma is measure and omega is symplectic form. But physicists may think another way. Yeah,
if it was on a manifold, I would not use sigma probably. But in the vector space, I think sigma is okay.
No, you can choose any letter you like, of course. Okay, questions, please, comments.
I'm sorry, I have one technical question.
Yeah, please.
In the one-dimensional case, can you apply some classical analysis result about rational approximations and find explicitly the algebra of functions that can be approximated by resolvents?
In the one-dimensional case, yeah, I mean the one-dimensional case is not too difficult, I think, if you look at the resolvents. And but what kind of approximation results you mean?
I don't know, something classical, like theorems from approximations by polynomials, by rational functions.
Yeah, I mean the one, yeah, you can do this because in the one-dimensional case, really the resolvents they vanish at infinity, right?
Yeah, exactly.
So their function vanishing at infinity. So you can use approximation results, yeah, like Sturm-Weierstrass or something like this. But this does not work in the high dimensional case, because if you go to in some direction orthogonal to some space, then they're just constant and they do not vanish. And that makes complications in the higher dimensional setting. So really the interesting case is the higher dimensional setting for the resolvent algebra.
I mean Runge theorem, yeah.
Yeah. Yeah, but to calculate the corresponding space, it's not so clear how that helps you.
Like some continuous functions, I don't know.
Okay, one more observation, but it's only in my taste. I think, Wolfram, that your talk was overloaded with a lot of material. It will be, from my taste again, advisable to speed down a bit your talk and maybe skip last part about infinite dimensional space, so we can more easily follow your mind during your talk.
Ah, the infinite dimensional case. Yeah, but this is the new part, so I want to say something new. Okay. Yeah.
Well, I'm not sure that everyone will agree with me, but it's just my opinion. Okay, anyway, thank you very much for exactly very good talk. And we hope to hear your talk somewhere in spring, sometime in spring.
If we have some
convenient for you and you will have new result and
if we have
can
some
tell us something
advances, yes.
interesting.